Yeah, so first of all, thanks a lot for giving me the opportunity to speak here. So this is the first time that I've been in Madrid for professional reasons, and so far it's been a very great workshop. So I'm very happy about it. And what I would like to do today is sort of offer a perspective on the sitter space in relationship to the swampland that might be slightly different from typical works that talk about the swampland and the sitter space. So this is based on a paper that came out together with Aalsma, and there's also some upcoming work with Sergio, who's here at this conference, and also with Watson. Okay, so first I will give you a bit of motivation of why I think it's a good time to take this particular perspective that I want to promote on the sitter space. And I will talk about this in a particular two-dimensional model of JT gravity in the sitter space, where I should stress that I view this JT gravity model really as an effective field theory, so not like a UV complete model. I will talk about a phenomenon that is known as an island transition, and I will argue how this island transition, how that is related to the swampland, and I will conclude with an outlook. Okay. So the motivation, so we all know that in, especially in recent years, I think that the instability or the stability of the sitter space in quantum gravity has been a subject of very intense debate. There are proposed constructions out there, there are proposed counter arguments, and I think the community has not reached a final conclusion on the verdict of whether or not metastable de Sitter space exists in the landscape. And we also heard some earlier talks about this subject. So what I would like to do is I don't want to go into the precise details of sort of what are the pros and the cons of like these precise constructions, or what are the pros and the cons of these precise swampland conjectures. What I would like to do is to take a slightly different angle and start from something that most people would agree upon and try to see if that poses any constraints on physics in the sitter space. So the angle that I would like to take is to start from a universal property of the sitter space that I think is widely accepted, which is the fact that we think that the de Sitter horizon carries a gravitational entropy proportional to its area, and somehow this should tell us something about the microstates of the sitter space. So if you believe in sort of a holographic principle for cosmological spacetimes, what this statement tells you is that there are microscopically a finite number of degrees of freedom. And what I would like to argue is that this fact, or this very reasonable assumption, poses constraints on physics. So what I would like to do is the following. Let's say that we're considering here a d-dimensional de Sitter space, and I write down its Penrose diagram. So then the two vertical lines here typically corresponds to the two poles on the sphere if you take a time slice. And we know that if we look at, let's say, one of these triangles, that corresponds to the so-called static patch. So if I take an observer that is living at one of the poles, it's the sort of the causal region of that observer. So sort of pictorially, what it means is if I take an observer there, that observer sees a cosmological horizon around a person. And what's an interesting fact is that this horizon radiates a Hawking radiation with a temperature that is given by 1/2 pi L, where L is the de Sitter length. And then there's an entropy associated with that horizon that scales with the area. Now, when we think about the symmetries of the sitter space, so when we look at the isometry group, so for d-dimensional de Sitter space, that is SOD, 1, and then we know that you can look at the, let's say that you write down the coordinate system that covers just a static patch. What you then find is that the isometry group of a static patch is smaller than the isometry group of the complete de Sitter space. So what that means is that I can look at the isometries of the static patch, so that includes rotations and a time translation. Then there are symmetry generators that mix different static patches. So this is just a different way of saying that the cosmological horizon in the sitter space is observer dependent. So this is a fact of life, but why is it important? Well, it's important because when we take this assumption of finite entropy, so particularly we work in a limit where, let's say, the Planck length divided by the de Sitter length is finite, what it means is that there's a finite entropy associated to the horizon. And in particularly, you would think that this would lead to a discrete spectrum of energy eigenstates. But then there's an old argument by Goher, Clement, and Susskind that this statement of having a discrete spectrum of energy eigenstates is inconsistent with having symmetry generators that mix different static patches. So what it means is that when we talk about de Sitter space quantum gravity, it cannot have the dissymmetries of classical de Sitter space. So in that case, you could say, does this mean that de Sitter space is in the swamplet? But are we even talking about if de Sitter space doesn't exist in the sense of its isometries? Then, of course, what you should keep in mind, what is relevant is that really depends on the time scale where these effects start to matter. So one way to sort of interpret it, this result of Cohere-Kleban Susskind, is that at long time scales, there can be non-perturbative effects that break the isometries of the Sitter space. And of course, you can write down different types of time scales. So some of the time scales that you might think are relevant is something like the Poincare recurrence time that scales exponentially with the entropy. So this will be possibly the longest time scale that you can consider. You can also consider something that you might call the page time that scales linearly with the entropy. Or you could also say perhaps it's a very short time scale, which would correspond to scrambling time or something that looks very similar as does the ECC. So what I would like to do, I would like to argue that some non-perturbative effects at least become important around this second time scale. In order to do that, I will go to an explicit model of JT gravity in two-dimensional de Sitter space. So if you will be interested in studying entropy in de Sitter space, for that perspective, it's very useful to go to this two-dimensional picture where we can exactly solve back reaction. So then you can write down the following action that can arise as a dimensional reduction from a higher dimensional theory. And what you then find is that there's a JT action like this. So there's a dilaton field phi, which gives some dynamics to this theory. And then there's a positive cosmological constant. And you can possibly consider matter couplings to this theory. Now, when you vary this action, you get these two equations of motion. So this first equation of motion is sort of the equivalent of the Einstein equations. And then there's an equation of motion for the dilaton that sets the Ricci scalar to have positive constant curvature. Now, when you take some coupling to matter, there will be a stress tensor. And then because we're working in two dimensions, these back-reacted equations of motions can be solved exactly. Okay, so let's say that we first consider sort of classical solutions. So we consider no matter coupling. Then what we get is we can look at different solutions to these equations of motion. They're typically parameterized by the different killing factors that are manifest in the different coordinate systems that you can cover the Sitter space with. So we are interested in using static coordinates. So here we have the static line element. And then one solution that you can get is just the dilaton being proportional to the radial coordinate. So you see this is manifestly invariant on the rotations and time translations. And if we view this JT gravity model as dimensional reduction, you can think of this phi as an area term. So that sense is logical to associate an entropy to the horizon, where the de Sitter entropy is now given by A over 4G, so kappa squared is 8 by G Newton, with a dilaton evaluated at the horizon. What's important, what I should mention, is that in this particular solution, you find that there are regions where the dilaton goes to infinity. And because of the way the dilaton multiplies the action, we can think of having a very large dilaton as being proportional to weak gravitational coupling. So this is really a feature that happens in two dimensions. Okay, so now let us include coupling to matter. And in that case, we can compute the effects of having quantum matter. What we'll do is we'll consider a coupling to a conformal matter sector, so a CFT. And for that, it's useful to introduce these Kruskal coordinates, which give a global cover of the Sitter. And then we need to specify a quantum state. So the natural quantum state in the Sitter space is the Bunch-Davies vacuum. And if you then write down the vacuum expectation value of the stress tensor in the Bunch-Davies vacuum and in Kruskal coordinates, this is just 0. So in that sense, you see that it's a vacuum state. Well, there's also an off-diagonal piece that is proportional to the central charge C of the matter sector and the metric. So this arises because of the conformal anomaly in two dimensions. However, these Kruskal coordinates are not a coordinate system that is natural from the perspective of the static observer. So we can use coordinates sigma plus minus that are related to the Kruskal coordinate as follows to express the stress tensor. And what we find when we define the normal ordered stress tensor is we find a result that shows that there's a thermal spectrum of particles. So it's proportional to the central charge again, and divided by the inverse de Sitter temperature. So what it means is that when you're working in this Barnes-Davies state, a static observer sees a thermal spectrum of particles. In that case, when you now solve the back-reactive equation of motion, you find the same term as before, but here written as in Kruskal coordinates, and you find a shift proportional to the central charge. Okay, so now I will argue that in this particular model, some sort of information paradox can arise. So here we'll just sort of sketch a very brief argument, and in a moment I will be a little bit more precise. So when you think about thermodynamics, the fact that the static observer sees a thermal spectrum of particles means that you can thermodynamically compute the entropy associated with that radiation. And then what you then find is that it scales linearly with time. So it's a growing radiation entropy. Well, this can potentially lead to a violation of what is sometimes called the central dogma of cosmological horizons. So a dogma is something that has more evidence than just speculation. It's not as rigorous as a theorem, it's somewhere in between. And the central dogma for de Sitter space reads as follows. When you think about a static patch of de Sitter space, the central dogma tells you that it should be described by some quantum system. We don't specify precisely what it is, but that quantum system should have a finite amount of states. So then when you see when this radiation entropy just keeps growing with time, what it means is that when the radiation entropy becomes bigger than the de Sitter entropy, the central dogma is violated. So if we think that the central dogma should be true, we therefore expect that around the time scale this happens, there should be corrections to semi-classical physics in such a way that the central dogma is preserved. And then you can easily see that the time scale where this would happen would correspond to the page time, which scales linearly with the de Sitter entropy. Okay, so let me now be a bit more precise about this statement in a very concrete model, and we can see how this is resolved by so-called island contributions. But first, let me explain to you a bit more in detail what I mean when I talk about entropy. So when we do semi-classical gravity, we are typically interested in what is known as generalized entropy. So when we think about a black hole, the way generalized entropy arises is as follows. Let's say that I take a black hole. We know that that black hole has an entropy proportional to its area, but then we can also consider the entropy associated with Hawking radiation that is being emitted from the black hole. So that would correspond to a matter contribution. And it's precisely this quantity, which is called the generalized entropy, that obeys the usual thermodynamic laws. So it's really, this is sort of the proper thing to look at. The matter entropy, the way you define it, is as the von Neumann entropy on a spatial slice. So it's a different way of saying entanglement entropy. So now we can, in recent years, there's been lots of development on sort of defining this generalized entropy. And by now there's a sort of nice prescription for it, how to compute it. So let's say that we, for example, take this example of a black hole in ADS space. We define some slice sigma that we want to compute the generalized entropy of. So what should we do? So there is some endpoint, possibly I, that's a codimension 2 surface. So when we want to define the generalized entropy of this slice sigma, what we should do is we should compute possibly the contribution of this area term associated with this codimension 2 surface, plus the von Neumann entropy on this slice sigma. And in particularly, what you should do in order to find this precise location of I, you should extremize this formula. So let's say that you're working in Kruskal coordinates, you take plus and minus derivatives and find the location where this finishes. And then if you find a particular extremum, we call that a quantum extremal surface, and that then gives the correct contribution. And in principle can happen is there could be possibly multiple quantum extremal surfaces, and this prescription that tells you that you should take the one that gives the lowest entropy. Now, I know you might wonder, so does this entropy formula give you the correct expression if you're thinking about the pure state? So pure state is defined by having 0 entropy. And you see that what can happen if you extremize this formula in a pure state, then this region I can shrink all the way to 0 size. In that case, there's no area term. And the von Neumann entropy is the von Neumann entropy of the entire Cauchy slice. So indeed, that correctly produces 0. But now, of course, we're interested in if to understand if there also could be non-trivial quantum extremal surfaces. And for that, it's useful to consider coupling to a Bath region. Okay, so now what we can do is we can define the entropy of some non-gravitational region R. And then if the system is still in a pure state, this suggests a similar formula for the generalized entropy of region R. Because what happens, let's say if we have a trivial quantum extremal surface and this sigma slice covers the entire region, then that entropy should be equivalent to the entropy of the radiation region R if we're working in a pure state. So what that means is I can write down an expression for the generalized entropy of region R that looks the same as the generalized entropy for sigma. And then what we can do is we can make use of purity of the state. So instead of writing the von Neumann entropy in terms of sigma, we write it in terms of the region R union I, which is the complement of sigma. And then you arrive at the following formula, which is known as the island formula, which is called this way because when you want to compute the entropy of the region R, it allows for a possible contribution that is disconnected, hence an island. So here I just gave sort of a simple motivation for this formula, but of course there are more rigorous derivations of it. And importantly, when you compute this island formula from a Euclidean path integral, then the way this non-trivial quantum extremal surface can arise is as a new saddle point that is typically non-perturbatively suppressed with the entropy of the system, but there can be some cases where it gives an order 1 effect. In particular, when the von Neumann entropy between region R and region I is small, then it's typically the island as an empty set that gives the dominant contribution, so that corresponds to the vanishing island. But when the von Neumann entropy between region R and I becomes large, then there can be a non-trivial island that gives the dominant contribution. And it's precisely around this time scale of the base time where RH is the horizon scale that this non-perturbative transition can take place. So this is really a non-perturbative correction to sort of semi-classical physics. Okay, so now that we understand the island formula a bit better, let us now try to apply this to the Sitter space and see what we get. So in the Sitter space, there's no natural bad region where gravity becomes very weakly coupled and we can sort of collect radiation. So in this upcoming paper, we have a proposal how you can introduce such a bad region and in order to very consistently compute the generalized entropy. And what we're doing is the following. You can consider a junction between a Winkler region and a de Sitter region. So you really think of this as a domain wall in order to basically replace the static wedge of the Sitter space by a Winkler wedge. In order for this to be a consistent solution of Einstein's equations or the equation of motion of JT gravity, you need to make sure that some junction conditions are satisfied. And then when you do that, you now have the upshot that you can now have Winkler wedges here where asymptotically gravity decouples, but you can use these regions to probe the cosmological horizon. So it really gives you some information about the Sitter physics. And then what we can do is we can go to these asymptotic regions. We can define some surface where gravity is weak, and then compute the entropy that is sort of being collected in these red regions. Okay, so what I mentioned indeed, so you need to make sure that this is a consistent solution. So you need to have to satisfy some junction conditions. So these are the two-dimensional analogs of the Israel junction conditions. Let's say that we're considering a junction located at the future horizon, x minus equals to 0. Then what you get is two conditions. So one of them is related to just the difference in the dilaton on both sides of the junction. So a square bracket means the difference between the two spacetimes. And then there's a second junction condition that tells you about the tension of this domain wall. So in this case, the two dilaton solutions in the Sitter space and Winkler space looks as follows. So in the Sitter space, it's the solution that we saw before. And in Winkler space, you have a solution that looks slightly different, where lambda is some parameters associated sort of to the JT model of Winkler space. Now we can use these solutions to compute the generalized entropy and see what we get. Okay, so the generalized entropy of these regions R is given by the following equation. So we have an area term, which in the JT context will be proportional just to the dilaton because you can think of it as an area. And then there's a term that is gives the von Neumann entropy, is proportional to the central charge logarithm, and then XIR means the difference between the x plus and the x minus coordinate between point I and point R. there's a UV cutoff that always appears in entanglement entropy. And then there are two conformal factors that are there because the way we compute this entropy is by doing a conformal transformation from flat space to de Sitter space. Now, this quantum extremal surface prescription or the island formula now tells us that we need to extremize this formula to find possible islands. And what you find is the following. So at early times, what you find is, in that case, there's not much entanglement between this dot region and the possible islands region. So in that case, you find a trivial island and you reproduce this linear growth of the entropy. But this is also the result that we expected from thermodynamics. However, at late times, what you now find is that this non-trivial island can appear, and that saturates the growth of the entropy. So its precise location is given by the following expression. So it's located at the future horizon and it's located at some positive value of x plus. And then when you compute the entropy on that non-trivial island, you find that the entropy saturates at twice the value of the de Sitter entropy. And the reason why it's twice the value of the de Sitter entropy is because we are computing the entropy sort of in both asymptotic regions. And what this means is that this island, the presence of this island really shows that there's this non-perturbative correction to sort of semi-classical physics in de Sitter space that appears at the time scale that is the base time scale. That appears linearly with the entropy. Okay, so in the paper we go one step further. Instead of just showing that entropy saturates, we also show that you can actually use a proposal like this to really decode information from the de Sitter horizon. So what that means is that what we can do is we can, in this blue region, we can modify the system in such a way that we're really collecting radiation from the de Sitter horizon, not throwing any radiation in. So in that blue region, there's only right-moving radiation. And this leads to an entropy that decreases a bit and allows you to recover information from the de Sitter horizon. And an upshot of sort of this Rindler gluing model that we have is you can really do this in a very controlled way where you can have back reaction effects on the control. So this consists of a very controlled way of recovering information from the de Sitter horizon, at least to the best of our knowledge. This is the first time that somebody has demonstrated that. Okay, so what is the main lesson of the fact that there are islands in this particular model? Or maybe more general, the presence of islands when you're computing entanglement entropy. Well, the main lesson is that when we think of the entanglement wedge of that radiation, so when we compute the entanglement of that radiation, the fact that it can be entangled with a region beyond the horizon is really some sort of holographic property that seems to hold beyond the context of ADS-CFT. And I think that's very exciting because it shows you that there are some universal properties that you can compute, for example, in ADS-CFT, but even they hold in spacetimes beyond that. So the fact that this happens this way, this entanglement wedge includes this region beyond the horizon, I think constitutes holography beyond the ADS-CFT correspondence. And what it really means is that entropy is sensitive to a notion of non-locality present in quantum gravity. So this is, I think, something that is quite deep because it really tells you something about some universal property of quantum gravity that goes beyond local Q of t. And entropy is sort of one way of probing this non-locality, but you might hope that there could be other sort of either observables or properties of a system that you might want to compute where this non-locality also shows up. So I think this is a very interesting question for the Swampland to try to understand, could there be other observables where these local properties show up? Okay, so let me finish with the outlook. So what I've reviewed today for you is a very simple and old argument that the de Sitter space is in the Swampland, in the sense that this isometry group cannot be realized in quantum gravity. And then it's an important question to understand precisely at what time scale sort of these effects show up. So this suggests certain corrections that are present when you think about semi-classical physics in the de Sitter space. And I showed you one particular example where this happens really concretely, which is when you're computing the entropy of a region in the de Sitter space. So what it means is that this generalized entropy is a observable of a system that is really sensitive to these type of corrections that appear in the de Sitter space. But you also might wonder if there are sort of other observables that are also sensitive to this type of effect. And I think this is a relatively unexplored area of the swampland, but I think it can have very important consequences, not just for the sitter space, but also when we think about black hole physics. So I hope I sort of encouraged you and motivated you. This is a problem that I think is worth thinking about. With that, I'd like to thank you.
Thanks a lot. So questions, Miguel?
Lars, thanks for the super nice talk. So I have a question. I find it really interesting this gluing you did between Rindler and the sitter, because from the Rindler side of things, it looks like, correct me if I'm wrong, but from asymptotically far away, it looks like you have really a black hole, something like that, which nevertheless is not crunching in the interior. Did I get it right? Yeah, actually. So I think one way sort of view this is this is really something that works in 2 dimensions. And what it gives you some sort of outside view of the cosmological horizon. But the field phi can take it as a proxy of the size of the 2 sphere, right? Like the way you get JT gravity into dimensions from pure Einstein 4 dimensions. So I can certainly uplift this to a 4-dimensional solution, right? Or... Yeah, that might be true. So what an outside observer would see is here there's a region indeed where the dilaton is large. You would say that's a large area. Right. Then if you're moving inwards, at some point this becomes smaller. Yeah. But then indeed asymptotically it increases again. Yeah, I find it fascinating because even in Schwarzschild de Sitter, right? Like you could think that this is the cosmological constant that is doing that. But in Schwarzschild de Sitter, the interior also crunches. Yeah, but here it's not. It's very interesting. Yeah, I think that's a very nice way of viewing it. Yeah, it's very interesting. Thanks.
Yeah, this is just a comment on what Miguel was saying, but I think there are like higher dimensional solutions that people consider, like when they look at the exotic compact objects, which are called gravastars, which are precisely what you're saying, where like outside of the horizon, you have a Schwarzschild metric, and then it's glued to a sitter solution inside of the horizon, which might be like. Yeah, actually, that's a good point. So we haven't really thought too much about sort of the higher dimensional lift. But indeed, like a model like that would be a very natural way to try to realize this in higher dimensions. Yeah.
How does the page time? How does the page time correspond to the TCC time scale?
Yeah. So maybe if I go all the way back. Okay, so TCC timescale is basically this, but there's a subtle difference. So TCC is typically formulated as L log m Planck over h. Entropy in 4 dimensions is m Planck squared over h squared. You would say this is a small difference. It actually makes a factor of 2 difference in the TCC. So it depends a bit, like if you think of the TCC, should it be a scrambling time or really just log m Planck over h? Okay, but the page time is scaled linearly with the entropy.
Yeah, thanks for the talk. I was wondering, in this type of setup, could you also work on things like the entanglement wedge reconstruction, quantum error correction, and the complexity in the recovery of the information from the radiation, since this is like the standard thing that people are trying to do with some Prescott protocol, but now it will be like adapted for the sitter in some sense.
Yeah, I think that's in principle something that you could consider. So because now you have this non-gravitational region, you can define a CFT there. So this island already tells you about the entanglement wedge. So in principle, you can try to think about. Yeah,
but I guess you need to like vary the regions that you are using for the recovery of information in the entanglement wedge to get like a good sense of reconstruction in that sense.
Yeah, so I guess in principle you could do is just sort of take different interval sizes and try to like look at how precise the information in the bulk is encoded like in that region. So that seems like something that's reasonable, I think.
Okay.
Okay. I think this is a good time to stop. Let's please thank Lars again.